Namaskaram. Welcome to my channel, Chemistry in a Nutshell. Today I am going to discuss about a topic which caters to the requirement of class 12 students. The topic is on the solid state. Now what I am going to do is, the current video which I am making out here is more of introductory in nature. I'll be touching through those topics which you have already done in classes prior to this class, that is in 9, 10, 11. You have already gone through this. So I'm just going to touch those topics. This is the introductory part, and then we'll concentrate more on topics which are relevant to class 12. So first of all, we'll begin with, remember the states, the different states of matter. That is, you have already gone across this, solid, liquid and gas, nothing much about it. And gas is a topic which you have already gone in much detail in class 11, I believe. Liquid also you have gone to an extent, you have gone through in detail, but the more detail was in physics compared to in chemistry. Solid is what is going to interest us, so this is the particular topic which we are going to discuss right now. So before beginning with this particular topic called solid, let's define what a solid is. So how do we define a solid? So solid is that state of matter where the constituent particles are binded together using a strong force of attraction. So I can just write the definition in a nutshell. So here the constituent particles are bonded together using a very strong force of attraction. So this is what is solid. And liquid and gas is quite obvious, you know that. It is comparatively much less in gas. To an extent, it's more compared to gas, but less than solid is liquid. But currently we are going to concentrate more on solid. So before getting into the details, let's understand the different properties which we have already studied in our lower classes. Properties of solid. Now the first one. Now we know that a solid has a definite mass, volume and shape. So that's the first property. Definite mass, volume and shape is the first property. Now what is the second property? The intermolecular spaces are very less, or they are closely knit together in such a way that the intermolecular spaces are very less in solids. So we can tell that intermolecular spaces are short. So the spaces are very less in solid compared to the other states of matter. Now what is the third point? The constituent particles Now when I'm talking about the constituent particles, what am I talking about? I'm talking about atoms, I'm talking about molecules, I'm talking about ions. So either of these constituent particles have a fixed position. So constituent particles have fixed position and oscillates in this mean position. And lastly, it is incompressible, or even if you are able to compress, it's very negligible. So it is incompressible and rigid. So these are the properties which we have already gone through in our lower classes regarding solid state. Now this particular science will have a lot of exceptions, no doubt, regarding it. So don't jump into a conclusion right now. What we are trying to do now is general in nature. Now see, in solid state, the constituent particles are held together with a very strong force of attraction. So they are very closely packed, they are highly packed. The intermolecular spaces or the spaces between the constituent particles is very less. So this has to be kept in mind, that it is very closely packed in a solid state. What is very closely packed? The constituent particles. Now, depending upon this, a solid has been categorized into two segments. So this is a very broad classification. One is called crystalline solid. The other one is amorphous solid. Now we are going to see these two, categories of solids. When I'm talking about crystalline solid, so in crystalline solid, there is a regular arrangement of particles for a long range. So the first point is regular arrangement of particles for long range. Now, I'll tell you the meaning of this. What actually happens is, whatever are the constituent particles, the arrangement is very regular. You can imagine something like this. Suppose this particular circles are the constituent particles. So we have a circle over here, 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 we have a circle over here. So again, we have now say for example, this is a constituent which is red in color, this is white in color, this is red in color, this is white in color, this is red in color. Similarly, I have one more constituent particle, this is white, this is red, this is alternately, I'm just writing it, this is just writing randomly. However, I have a particular pattern of doing it, red, white, like that. Again, say for example, I'll go for the third line also. Red, white, like that. You see, I am following a particular type of arrangement, and this arrangement is same throughout the entire constituent of the solid. When it comes to amorphous solid, the arrangement is not regular as with respect to crystalline solid. Of course, there are certain textbooks which even refer to this as irregular arrangement. However, to an extent it is regular. So regular arrangement of particles for short range. So here what we have is something like this. Suppose this is red, this is red, this is white, this is again white, this is red, this is red, white, again red. So you can see that again we may have some white, and red, so like that. So you don't have a particular set of arrangement as in case of crystalline solid. It's not regular at all. It's more of random in nature. So the constituent particles are more of random in nature in amorphous solid compared to the crystalline solid. So this is one of the primary characteristics which makes them differ from each other. Now, because of this haphazard arrangement, it makes it a very weak solid. So that is why you'll always find crystalline solids are very hard in nature, whereas amorphous solids are weak in nature. I'll give an example, a chalk. You must have seen a chalk in your classroom, in your school. You must have seen chalks, which is used for writing on the board. It's calcium carbonate. The same constituent, the same material is also there in marble. But have you seen marbles are very strong? The reason behind this is the marble is crystalline in nature. It's a crystalline solid. whereas chalk is amorphous solid. So you can understand what is happening internally. Internally, in crystalline solids, that is in case of marble, the constituent particles are arranged in a very regular manner. It has a regular arrangement, hence making it much stronger compared to the amorphous solid. That is, in our case, I am talking about a chalk, which has a very weak force of attraction compared to the crystalline solid force of attraction because of this haphazard arrangement. So amorphous solids mostly are weak solids. The next point, the second point. Crystalline solids are called true solids, whereas amorphous solids are called pseudo solids. Or supercooled liquid. Interesting. So crystalline solids are called true solids because of the regular arrangement of the particles. We call it true solids, whereas amorphous particles are called pseudo solids. That is, this arrangements are because of the way it is arranged. It doesn't make it very strong. It makes it quite weak, and hence there is a possibility of disintegration. You must have seen a chalk can easily break away. So there is a possibility of disintegration. That is why this kind of solids are also called supercooled liquids. So that is what you see, what happens with even glasses. Even glasses are amorphous solid. For a course of time, if you notice carefully, it takes an enormous amount of time. I'm talking about a normal glass. You'll find that if you keep it standing, you'll find at the bottom it gets thickened. The reason behind this is, since it's a liquid, in the course of time, it starts flowing and gets concentrated at the bottom. So that is why these amorphous solids are also called supercooled liquids. And now I'm going to talk about the next characteristic. Now the third characteristic. This is I'm discussing a comparable characteristic of both a crystalline solid and amorphous solid. However, please remember, we'll be concentrating more on the crystalline solid in the course of time. We'll be dedicating more ourselves to the crystalline solids. So you need to understand crystalline solids quite well. So the next characteristic is the melting point is very sharp in case of crystalline solids. So the melting point is quite sharp, whereas in amorphous solid, the melting point is always in a range of temperature. I'll tell you the meaning of that. Now, say for example, you have a crystalline solid whose melting point is 120 degrees. I believe you remember what a melting point is, where the state changes from solid to liquid. So suppose I have a crystalline solid whose melting point is 120 degrees Celsius. Now remember, this is very sharp. Now I believe the melting point is at that particular temperature, the state is going to change. So here, when I tell it is 120 degrees Celsius, so at 120 degree, the entire solid, so suppose you have a mass, a solid mass whose melting point is 120 degrees Celsius, at that particular temperature, the entire mass is going to get converted to liquid. It's very sharp. Whereas, in case of amorphous solid, there is always a range of temperature. Say, for example, you have a solid mass which is amorphous in nature, and here we have a melting point ranging from 100 to 150 degrees Celsius. So this entire range will be used to convert that amorphous solid to a liquid state. So you'll always have a range of temperature where the solid is getting changed to liquid. For example, the chair which you are sitting now currently. Maybe it's made out of plastic. Now you must have seen in a plastic what actually happens. In a plastic, what actually happens? That first of all, when you start heating, it just softens. It softens itself. And after it softens itself, only then there is a possibility of it getting into a liquid form. So plastics are a kind of amorphous solid. The next characteristic is crystalline solids are anisotropic in nature. Crystalline solids are anisotropic in nature. And I'll tell you the meaning of this, do not worry about it. Amorphous solids are isotropic in nature. Now, when I tell anisotropic in nature, that means it has different physical properties in different directions. So we have different physical properties. I'll just write this. Different physical properties in different directions. Whereas in isotropic solids, in amorphous solids, it is isotropic in nature. It means it has the same physical characteristic, almost. In different directions. So I'll just tell you what is happening over here. This entire concept is coming right from the beginning, where we started with, the regular arrangement. So once again, let's get back to that particular figure, where we were arranging the constituent elements. So we have a red particle, then we have a white particle, a red particle, a white particle, a red particle, like that. Again, we have a white particle, we have a red particle, we have a white particle, we have a red particle, and we have a white particle. So I'm just writing alternately, again, red particle, white particle. So we have a regular arrangement out here in case of crystalline solids. Now, you must have heard about refractive index. This you have studied in physics, refractive index. So here, say for example, in this particular arrangement, if I move in this particular direction, now you see what is going to happen. First, if you look at the particles, what is this direction going to find? These particles in the form of. So first the red constituent particle, then the white, then again the red, then the white, then the red. So this is what it is going to go if the direction goes this way. Now, say for example, I start the direction this way. Now look at the constituent particles. It first goes to red, just like this, white, just like this. However, in the third case, which was red, in this particular case, it's white. Now look at even at the constituent particle just next to it. If it passes from here, we have first a white particle, then it goes to the red particle, then it goes to the red particle. So in every direction, it will always find different constituent particles. That is when we tell that the physical properties are different in different directions. That is what it means by anisotropic in nature. Whereas when it comes to isotropic in nature, it is always seen because there is no proper arrangement. I can give you an example to explain, what I mean by same physical characteristic in different directions. You see, it all began with isotropic in nature. Amorphous solids are not having a regular arrangement of the constituent particles. Now, having said that, when I say that, say for example, you have a marriage party, and in this marriage party, you have different set of people. There are girls, there are boys, there are few gentlemen, there are few ladies, who have come over here. There are even kids who have come over here. Now, if they are all, standing or sitting or in a haphazard way, they are mixed with each other, the entire crowd is mixed into each other, it's very difficult for someone to come and find out someone. Whereas, if you organize this, say for example, we'll have a set of row where only, men are there. And then we'll have one set of row where only women are there. There'll be one set of row where only kids will be there. So now it's very difficult to find out someone because the arrangement is, regular. Whereas if you just mix it up, in whichever direction you try to find out, it will be altogether the same. So in that sense, it is isotropic in nature. Okay, now I am going to talk about different type of crystalline solids. Let me categorize them. Types of crystalline solids. So it has been categorized into 4 groups. The first one is called ionic solids. The second one is called metallic solids. The third one is called covalent solids. And lastly, we have the molecular solids. Now let's go through this characteristics, the different characteristics. We are going to concentrate more on the ionic solids because that is what we are going to study more. We are going to put more stress into ionic solids. Before any kind of discussion, let's go through the different characteristics of these different types of crystalline solids. So first of all, let me talk about the different type of constituent particles. The first characteristic which I am going to talk about is the constituent particles. Now, for ionic solids, obviously the constituent particles are ions. And when I am talking about ions, of course, there are 2 types of ions, that is cation and anion. So the constituent particles for ionic solids are ions. Example is sodium chloride. You must have seen this. Na plus and Cl minus. Those are the 2 ions in sodium chloride solid. Next, the constituent particles for metallic solids are metal atoms. So the constituent particles are metal atoms in case of metallic solids. And for covalent solids, it's non-metallic atoms. So for molecular solids, you have molecules, atoms of same type. So this is with respect to the constituent atoms, constituent particles. The next characteristic which I am going to talk about is the force of attraction. You see, the force of attraction in ionic solids are obviously electrostatic forces. Because of the ions present, the cation and anion, remember, it's also called ionic bond. We call it ionic bond, however, internally, obviously, it's electrostatic force. So the force of attraction in ionic solids are electrostatic forces. For metallic solids, the force of attraction is, for metallic solids, the force of attraction is metallic bond. You see, the metallic bond is a bond between the kernel and electron. So here you see metallic bond, it's a bonding between the kernel and electron. I believe you have studied this in class 11. And for covalent solids, it's covalent bond. And for molecular solids, it's van der Waals force. All this you have already studied in class 11, the different type of forces in different type of solids. Next we are left with melting point, melting or boiling point. So for ionic bonds, obviously the melting point is very high because there is a great ionic bond playing between the ions. So it's you really require a lot of heat to be given to break through this electrostatic forces, okay, and to bring the solid into a molten state. For example, you need to really have a very high temperature to bring sodium chloride into its molten state. For covalent, for metallic solids, even this is very high. For example, say iron, the metallic bonds in metals are very high. And then for covalent bond, it's very high. The melting or boiling point is very high. Although you see the force of attraction of ionic bond is much more compared to the covalent solids, yet the melting or boiling point is very high. And for molecular solids, it's low. Now the last characteristic among these different types of crystalline solids is conductance. So for ionic solids, conductance are only present in molten state. So only in molten state you will find any kind of conductance. Remember, when it is in, suppose say for example we take sodium chloride in molten state, it will get ions. Only when we have this charge carriers, only then it is possible for it to have any kind of conductance. And for metallic solids, it's highest. So you must be knowing it. Iron, zinc, copper, all this have very high conductance. Now let me talk about this. The metallic bonding. I already talked about the metallic bonding which occurs between atoms and the kernel. For example, let's go for iron. Remember iron, Fe. It's written as, metal always have the capability of, giving away electrons. It has free electrons. It has the ability of, giving away electrons. So if I take iron, Fe, it has the ability to, give away electrons. So if I take 2 plus, we are left with 2 electrons. If I take Fe3 plus, I'll be left with 3 electrons. And so you must be knowing this. Now what happens is, suppose if I take a iron crystal, so how does it look like? Fe2 plus. So this particular crystal, so now it might occur to you that since they are all positively charged, they will be repelling each other. So how can they remain in the form of a crystalline solid? What actually happens is this free electrons, actually what happens is it starts moving like a cloud around it. We call it a cloud of electrons. It's like a river flowing through these atoms, flowing through this kernel. So this free electrons, so how many free electrons are there? 2, 4, 6, 8, 10, 12. So this 12 free electrons moves like a cloud all over this, like a river, So we call it electron cloud, which moves in and around this Fe2 plus, and it forms a kind of a bond in metallic solids. And therefore the conductance is highest in case of metallic solids. It's low for covalent solids, and even for molecular solids it's low. And now I'll give you a few examples. Like for ionic solids, examples are sodium chloride, NaCl, KCl, ZnS, CaF2. And for metallic solids, we have Fe, Zn, Cu, Al. These are examples of metallic solids. For covalent solids, examples of covalent solids are we have silica, we have diamond. So you can take diamond. So the bonding between C and we have a bonding between silica, and then we have the molecular solids. Examples of molecular solids are CO2, I2, P4. So these are examples of molecular solids. Of course, exceptions will always be there, but what we are studying is general in nature. The next part will be, dwelling more deeper. There won't be much of theoretical aspect to it. It's more of practical and more interesting topics will be coming up.